In this part of the tutorial, we are going to focus on offline model verification. To do that, we are going to introduce first our modeling format RoAML, used to describe our system and environment. Afterwards, we are going to show how to use AS2FM to convert the RoAML model into a format that can be digested from a format verification tool, that in our case is Johnny. And finally, we are going to use SMC-STORM to perform the verification of an LTL property on the model of the system. For our particular example, we prepare 3 models of our environment, each one posing increasingly complex situations. In particular, the first simpler model is word.asc.xml, where there is only one location where the object can be, and the robot knows exactly where to go for picking it up, and all actions are deterministic, meaning that there is no failure in this particular model that can happen. The next word is a bit more complex because it has multiple locations where the object can be spawned, so the robot needs to find where to go in order to pick the object. But again, here all actions are deterministic. And the last one is word multiple locations with failures.asc.xml that introduces possible failures in the system, simulating what happens when the robot doesn't manage to perform its action. For this tutorial, all the commands will be executed in a Docker container. So in order to start, we need to execute this docker compose command in the terminal. And then we can access using VS Code the particular instance of Docker container that was created. Once here, you can find the tutorial files in this folder. And what we are interested in is the content of the RoAML folder that contains the RoAML models together with the policies that can be executed from the robot that are behavior tree files, the environment that is located here, and all the plugins that are executed when the behavior tree is ticked. The entry point of RoAML are the main XML files. As an example, let's look into the main XML file here. We have the parameters that define some parameters of the model that are not defined in the other files. For example, what's the maximum time that can be reached from the model, or what is the maximum size of an array that we expect to have in our model. Then we have the data declaration files that are defining the custom data types, so custom structs that can be used in our model. For example, here we have coordinates and object locations. Then we have the behavior tree part that contains the behavior tree that is executed in the model, that is in the format of behavior-tree.cpp, like the one here, and can be also opened using root, for example. And next to it, we have the implementation of the different behavior tree plugins that are executed within the tree. So if you open again this behavior-tree.xml, we have detect object, and we can find the implementation here, detect object. And these plugins are implemented using the AS2XML format. That is an extension of the AS2XML format, where we include, for example, ROS entries, behavior tree specific entries, for example, the behavior tree ports, and also behavior tree specific commands like tick, hold, and then also the return of a tick. Finally, opening again an XML file, we have the different nodes that are executed in our model. In this particular example, we have mostly the environment and skills that are then implementing particular functionalities of the system. If you look at the word that is in the environment folder, what we have is, again, a bunch of ROS declarations for actions, topic publishers, and time grades. And topic publishers are very important here because it allows us to expose the status of the system, and therefore we can then rely on this information for writing our LTL property. That will be the one we want to verify later. And this is also matching with what the monitor will do, because it needs something to check in order to detect what's happening in the system. Then here we have the data model that contains all the variables that are storing the current status of this particular node in the system. And then all the different states. Here we have the initial state that will, for example, spawn the object at the location fridge and assign the parent word, that is the frame where the object is living. For this particular model, it can be either a word when the object is on its own somewhere, located somewhere, or robot when the robot picks up the object. So that object is not anymore related to the word, but is in some particular time related directly to the robot. And then we can define what happens when we receive a goal in the navigate action. And so here we describe get the goal ID, set the location, and then signal that the goal was accepted. And if you want more information, you can dig deeper into this file and understand what's going on. And the final part of the RoAML model is the properties file. In this particular case, we wrote the property directly in Johnny, and you can find this in the properties folder. And here, this is a JSON file where we want to have the snack at table. So this property will just check whether finally, so at some point along the execution of the system, in the topic location message, we have the value 4.0. So this object location is, so topic object location message contains the field X with value 4.0, the field Y with value 2.0, and it is also in the frame word. This means that the object is placed in the word at the coordinates 4, 2. Now, to proceed with our tutorial, we can see how to use AS2FM in order to get a model from the main.xml file. To do that, we can open terminal, and we can see here we are in the Docker container, and we can navigate to the folder RoAML, this one, containing the main XML models. Once here, we can use the AS2FM ROM to Johnny in order to generate a Johnny file, like this one. And here you can see that AS2FM goes through all the different ASCXML files, loads also the resources here for the standard behavior tree plugins that are, for example, doing the OS success, if-else, reactive sequence, and so on, and makes a Johnny model out of all this information. That is this one. This file is huge because it's just a complete JSON file containing all the information that are required for executing the model and synchronizing all the different parts of the models together. So we don't have to get into the details of this file. But what's important now is that we can use SMC-STORM in order to see whether the model works or not. And for doing that, we just use this command here, up to the batch size, because we don't want to generate the traces, at least not for now. So here we are passing the name of the model, the property that we want to verify, and some other additional flags, for example, to not cache the states that were explored, because otherwise this will take too long, and additionally, This is not working for models containing float variables. How many threads we want to use for expanding the traces. In this case, we do this with 10 threads, where we want to see all the statistics that were calculated from the traces that were generated, and also how often to update the statistics in order to determine whether we are finished or not. In this case, every 5 traces. And you can see here that the model always succeeded, meaning that the robot was always able to navigate to a location. If you look at the model, we can see here the robot was always able to navigate to the fridge, detect the object, pick it up, go to the table, and place the object. Now we can try to make a model of the more complicated word. In this case, these main locations. These main locations has 2 differences compared to the one before. We use a different behavior tree that can handle multiple locations and loads the word multiple location to the AS2FM. Apart from that, everything else stays the same as the other model. So here we use main location.xml, and also here we just generate a different output Johnny file. And again, we can run SMC-STORM using the new main locations.Johnny. And here there are some failures, but in this case we know they are not so important because those are due to a small problem, that the synchronization of the tick and the return value of the tick when you write into the blackboard is not really working all the time. But there is an issue of an AS2FM already that's due to the conversion into Johnny. But in general, this is 99.5% working correctly, this model. This means that also in this case, the system is working as we are expecting. And then let's look into the more complicated word, the one that has failures. So in this case, we have the first model here, where we are loading the word multiple locations with failures model, but we are using again the same behavior tree as the one from the model we just verified. This means that even though there are failures in the model, we are not handling this in the behavior tree. So let's try to generate this model. And let's run the verification. And in this case, you can see that the system is failing far more often than it is succeeding, highlighting the fact that this is often the case, that the robot is not able to successfully bring the robot to, is not able to successfully bring the snack to the table. So this is succeeding only 14.5% of the times. What we want to see now is the reason behind these failures. And to do that, we need to generate traces. And here, the additional part that was in the SMC-STORM command comes handy here. So we just tell SMC-STORM to store all the traces into this folder. In order to not generate too many, since we know that this fails quite often, we can also add a max number of traces, and we put it to 20. And here we have our traces. You can see that you can easily distinguish between traces that failed with the not verified end of the name and the traces that did not fail, so the verified ones. You can either inspect this manually, but I do not recommend it because they are CSV files that are not great to read, even if you are opening them with Excel or other nicer visualizer for CSV. Or you can use Plot Juggler, that is a plotting tool from ROS that is very useful also for plotting data from CSV files. And for doing that, you can just do to run plot juggler, and you can also tell directly which file you want to load. That in this case is trace 25545 underscore 00001 not verified.csv. And we want to have the row number as x-axis and then load it. Once we loaded our CSV file, we can investigate everything that happened into our trace. For doing that, we can simply drag and drop the different entries that we can find in this block into the plot area here. For example, we can plot where the robot drove over time, and we can see that here, for example, the robot drove first along the x-axis and then along the y-axis. Or we can plot where the object was spawned. So we can see here that the object was at -2 regarding the x-axis and then also at -2 on the y-axis. So if you put the four of them together, we can see that the robot dropped somewhere, but that somewhere is not the same somewhere where the object is located. So we can investigate what happened with the behavior tree. The name of the different behavior tree plugins are shown here. You can see how they're mapped from the plugin name to a number. And this number is then important further down because this is how we can map them to the response that they provided here. This is the force sequence. You can see that it went up to 3, that means running, and at some point it dropped to 2, that means failure. Then we had the second one that was not shown above because it's just an inverter. And we can see that here this went to 1, that is success, and then, this was given to the inverter, and the inverter then applied failure here. And then we can keep pulling in, basically, these different plugins in order to understand how the system worked. So we have PT1002, that's also failed. And then we have PT1003, that also failed. 1004, that instead succeeded. And we just pulled some more in. 1005 failed. 1006 was never ticked. So we never reached the plugin number 1006. And if you go again up, we can see that 1006 was not visible, okay. But 1005, that is the one that failed the last, is the navigate to location. Meaning that this is what failed here the first time. So the robot exceeded 1004, that was successful. So it means that it was able to get the next location, but then when it tried to navigate to the object, this failed, meaning that then the sequence where it's located, this plugin, failed as well. And then we can also see that there is BT plugin 1008 that is picking up the object, and this is also failing, and I can show this in the plot, and I can also explain why. This is BT 2008, and this is also ticked at some point and then failed. And regarding the why, we can find this out in the behavior tree here. So what we execute here is get next location. This was succeeding. Then we try to execute navigate to location. This is what fails. This fails means that the sequence fails, and means that also this repeat fails. But once this fails, this goes to the inverter, and the inverter tells you, oh, this failed, then success. This then makes this sequence step further to the next peak object. That is what we just checked. That is ticked, and then it fails because the object is not set. Or anyway, it's not. It's not set, so it's not detected. And then once this fails, the whole sequence fails, and then this results into the behavior tree failing. So we know now that our actions can fail, and we have to maybe try them again in order to make sure that the system can more reliably execute. And we do this with this new behavior tree extension, where we wrap the possible failure plugins, that are failing, into a retry until success. And then we give it a number of attempts that can be 3 or 4, depending on how confident we are that this action is succeeding or failing. And we can then call again our converter here, and in this case, what we want to do is we can remove. And what we want to execute now is this particular main locations with failures. So main location with failures, then main location success, and we can run again SMC-STORM with main locations success. And okay, this was just 20 entries, so not many. And also we don't want this traces folder now, so we can remove this. And the just can go back to 5. And you can see that there are still some failures, because I mean the system can fail in the model, in the word model. So you can try multiple times, but if you are very unlucky, this number of times are not enough, and then you result into failures. But by simply adding this particular block of retry until successful, we are brought up from 14.5% to 96.8% the probability that the system is working correctly. And this is all for what concerns this tutorial.